Well, so we go back to what we started with the transformation in principal coordinate. So the model or what is called the model approach for the continuum. We make very simple examples, but the methodology can be applied in a very wide variety of configurations and the complexity of the systems. We make reference to the cable or the beam along the x-axis. Here I show S in order to say that there is a tension if it is a cable. If it is not a cable, if it is a beam, it could be that we do not have the tension. The drawing with this S here is a bit misleading. Just keep in mind that in case you have this tension is not applied here, is applied on the constraint, of course. All right, but just to keep in mind that we could have a tension. If you are tensioning the cable or the beam among 2 inches here, you do not have to apply a tension over here. It is the constraint that is moving in order to pull the cable. But in order to have the visual idea that we could have a tension, I show the arrow there. Well, so we were working with the energy quantities. The energy quantities are the kinetic energy, potential energy, potential energy for the beam. I don't go into details about that in order to demonstrate why we can write in this way the potential energy of the beam, because it is a matter that you already did into the structure course. In case someone didn't make it, I can stay here at the end of the lesson in order to explain, in order to give some more details about that. But we save the time because it is within the program of what you did already. There is the demonstration that this is the way in which we are writing for the bending beam the potential energy in a deformed configuration generally. It is more interesting because maybe you will not do in other courses, or you didn't do in other courses, to have the idea of the reason why we can write that the potential energy of the cable that is tensioned could be written in this way. So where this is the tension along the cable, S, the tension can be a function of the space, of the location. So in all what we are saying in this very simple theory that we are developing, we do not have to force the condition of having the properties of the beam or the cable constants. So we can work with mass that is changing with the coordinate x, geometrical properties of inertia that are changing, and also the tension that is changing. So it is not, so the theory is working without this simplification hypothesis. And so for which reason we can write in this way. It is interesting, in my opinion, because in order to have the idea of the way in which we are dealing with the infinitesimal quantities, when we can forget that there is a modification into the quantities when we have to consider. So, for example, and we will focus into this. So, in order to write a potential energy when the cable is moving away from the rectilinear configuration, we have to say that moving from this straight line configuration, it is increasing the potential energy, okay? Of course, it already has a potential energy because someone pulled the cable, but the reason why it is vibrating is because when it is moving away from the equilibrium configuration, something is changing. For example, the potential energy is changing. But then also something else is changing. The kinetic energy is changing. In order to say that the potential energy is changing, we have to say that the cable moving from this, the dx portion of the cable, when it is inclined with a tangent dy over dx, it is longer. It is obvious that it is longer, okay? But in order to say that, we are saying that when the cable is vibrating and has a shape that is not rectilinear, it has more energy in terms of potential energy, but it is longer. And if it is longer, we are saying that the tension is not constant here. It has been elongated, and so the tension is different, is moving away from the value that it has when it is in a straight line, all right? So there is a contradiction there. The contradiction is that also applying this theory now, we are saying that the tension S could be function of the location X, but is not function of the displacement Y. So this is a contradiction because we are saying it is moving away from the straight line, it is inclined, it is longer, and we are writing how much is longer, and so it has more potential energy. But then we are contradicting all of that because we are saying it is almost constant. And doing this calculation, calculating the potential energy, we are saying that the cable is becoming longer of a quantity that is the difference among the, so if I call this dl, what we are writing is dl equal square root dx square plus dy over dx, all right? So this is the Pythagoras theorem. So this quantity square plus this quantity square makes this quantity square, all right? And so we are writing dx square and so on, all of that square. And so we write dl equal dx square root 1 plus dy over dx square. This is a square root 1 plus epsilon. Okay, so dx, dl. The square root of 1 plus epsilon, written through the Taylor expansion, is 1 plus epsilon. Okay, 1/2 because I'm making the first, so I calculate it into 0, so it is 1 when epsilon is 0. First derivative, 1/2, and then the square root below the fraction line, calculated with epsilon equal to 0. And so it is 1/2. 1/2 multiplying the derivative. So it is the expansion, the Taylor expansion stopped at the first order. And so it is like that. And so dl is equal of dx multiplying and here I write almost equal. Okay, so epsilon is this object here, the full object with the power of 2. This is epsilon square. And so we write here dy over dx square. And so the amount of the elongation that is undergoing the elementary element, the infinitesimal element dx is dl minus dx equal, let's write it in that. If there is some mistake, please tell me. So we say that, and here is the point. We are calculating the increase in potential energy due to the deformed configuration of the cable that from the straight line is assuming a shape like that, all right? And so we are calculating how is increasing the potential energy. And we say that the potential energy is increasing because the let's say, constant axial action that is not changing because it is moving. So we are considering that the axial internal action is not changing because of the movement, is constant. Instead, it is a little bit changing, but it is an infinitesimal of superior order. And so we are considering that the first order quantity is the work done by the axial action that is undergoing an elongation of the element. So the element is of having length dx is undergoing an elongation. The axial action as function of the linear coordinate is working because this force is moving of a quantity that is the elongation. And so we are calculating the increase in potential energy, saying that this force that is almost constant, but it is large. It is large and it is a little bit changing, but so we are calculating the first order quantity. So the large part undergoing the small movement. There is a second order. There is the change into the actual value of x undergoing the small movement, but it is small times small. It is small power of 2, and so it is negligible. All right? And so it is important that you are very confident with this way of doing things that is a little bit contradictory, but it is not contradictory. It is the way that we should have learned using the infinitesimal calculus done into mathematics. Everything goes there. There is nothing different. It is always down there. What we do in mathematics is making all of that totally obvious, simple. All right, well, so it is clear for which reason we are writing this potential energy of the cable in this way. In my opinion, it is an interesting example because I think that you didn't encounter earlier. And it shows this way of considering things constant but also changing. And of course, we mentioned several times that we have to keep in mind that when the cable is undergoing a movement, so when the cable is going away from the straight line, it is longer. The tension is a little bit larger, some percent, depending on the amount of elongation it has. But let's go back into what we are saying. Working with the potential energy, we are assuming that this quantity as function of x is constant with respect of the movement. It doesn't change. can be distributed differently with x not constant there, all right? Well, so I cancel all of that. We do without spending much time. We are using the same methodology that we used for the kinetic energy. And let's go to the final results. There was a mistake here. So what we are doing, we are working with the derivative of y, of the derivative with respect of space, right? The derivative of y with respect of space, okay? That is the derivative phi first multiplied q. So of course, y is equal to the vector of the modes of the eigenfunctions of the vibration modes multiplying the vector of the principal coordinate. And if I take the derivative with respect of space, it makes phi first, so d phi over dx. And so we have this phi first multiplying q, that is the representation of dy over dx squared. We have to make the square of that, and we go back to what we said. We say that this quantity is a scalar, so is a product of functions times other functions, but it is one single object. And so it is a scalar, and the square of this scalar is, and the transpose of the scalar is a scalar, and so it is useful to say that the square of eta is instead written easily like eta transposed times eta. Eta transposed is writing this quantity like q multiplying phi, and so finally what we write is the same old story, 0L So the square is written like as the vector not transposed. So this is the column multiplying the vector transposed, that is the row, integrated over the x, all of that multiplied by q, function of time. This is n, this is an object n, and this is a square matrix that is n, and the rank is n. So we moved the integral into the matrix. It is exactly the same methodology that is applied for the kinetic energy, just we are writing this quantity as the product of two vectors, and then it is just the movement of the vectors and making a column vector multiplying a row vector that is making a matrix. And this matrix has at the location ij the product of the ith and the jth element of the column, of the vector itself. And so the methodology is totally repetitive, and we can write also the potential energy of the beam. So I prefer now, I write in a different way. So I write not the vector multiplying the vector transposed, but I write the ij element of the n by n matrix. So this object here is a n by n matrix where the ij element in the ith row and jth column is made by the product phi I, so the ith eigenfunction, second order derivative multiplying the jth eigenfunction, second order derivative. It is exactly the same methodology that was done for in details for the kinetic energy, and I suggest that you make practice with your hands in order to repeat the calculation, in order to confirm, in order to be very confident in this way of making the calculation and the representation. So what is relevant is to say is that both the kinetic potential energy, kinetic energy and potential energy are written as a quadratic form. So a quadratic form where you have the matrix, the vector, the transposed vector, and you have 1/2. So this is the structure. It is always the same repetitive structure. Kinetic energy, it has this structure, and into here you have q dot function of time. So the vector of the first order derivative of the principal coordinates that newly introduced. In case you're writing the potential energy, instead, this is the vector q, not the first order derivative, all right? So now I'm writing without the dot. So I'm writing q, that's it. And this is function of time, all right? And into here, there is a matrix, n by n. We defined the ij element of this matrix Then, with the full generalities, we will demonstrate, but we already know it is in the A, that is like that this matrix is just diagonal. We have just the I element, the ij element, in case I is different than j, are null, and we can demonstrate that the reason why they are null is because we are using for the representation in principal coordinate a base of functions that is a very special base of function. It is the base of function that is satisfying the partial the derivative equation that is stating the behavior of the beam. And we will make the demonstration. So this is the framework in which we are moving. And so we have the idea of what is working, that this is the structure of the quantity of the energy quantities for the examples that with which we are playing. All right, next. Next, we have to put all of that into the Lagrange operator. There is a quantity here that with which we didn't work. That is in the virtual work of the external forces. So we have here the external forces, a distributed force function of space and time, a concentrated force or a set of concentrated forces function of time, a moving load, a constant force that is moving with the velocity. It is strange. Right? The idea is that we can treat all of that in a very, very easy way, writing in the energy approach of Lagrange the virtual work of the external forces. And we will work on that at the very end. First of all, we have to make sense to understand what we are saying with this symbology. I already explained to the people who did the second year of applied mechanics. Is it here some of you that was my student? All right, one. So we did the demonstration of the Lagrange equation. So it is very easy for you. It is once in the life could be interesting to do something that you are using for all your life, and not to believe to what the other people are saying to you to believe. It is very important not to believe everything. Very important, and to trust in case you are doing with your hands. All right, what do we mean when we say derivative with respect to a vector? We are saying that if I have a constant So let's make an example, very simple. So the object with which we are working here, the kinetic energy is the mass matrix Q dot transposed, not transposed, 1/2. So, all right, this is the kinetic energy. So let's focus on this quantity multiplying this vector. This vector is this vector here. And what is this quantity here? It is a set of scalars. It is a vector. It is a row vector. Because if we make the row vector multiplying the matrix of columns, we are building a row vector, all right? And so this object here, we have to look at that like a set of, let's say, numbers, but they are not numbers, they are also functions, but so it is a vector of object that is multiplying another vector. When we write the derivative, the partial derivative with respect of the vector q, we are saying that I write an object that is made by 4 objects, that is the derivative with respect of q dot 1, that is what? This constant here. And so when I write the partial derivative with respect of the vector q dot, I do the first. I am operating, I'm making the partial derivative n times with respect of the first, the second, the third, and the last of the column, making a row of objects that is a vector. And so making the derivative with respect of q1, the result is c1. Then there is another object. Derivative with respect of c2. We are repeating, we are making the derivative with respect of a vector, we are building a vector that is made in this way. It is a procedure. So this symbol, derivative with respect of a vector, and is telling you have to make this procedure. And so I do the derivative with respect of the second object, that is C2, all right. I'm making the derivative with respect of the third, it is what? C3. I'm making the derivative with respect of the 4, is C4, all right, simple, okay? And what I did is a partial derivative of this object, the total, and this total is this object plus multiplying this object with respect of this vector. And so we are discovering that as the vector q is staying here, the first thing that we can do very easily is to say that a portion, 1/2 of the total, is made by this quantity here. So q dot mass matrix, that's it, finished, 1/2 plus multiply q dot. That's it, finished. Okay, the partial derivative with respect of with respect of q dot is this object. We are going down here. So we are saying I am representing this object here as it was the first part of the quantity multiplying this vector. I am keeping the attention that I have the vector of the variable with which I have to play with doing the derivative. I say that I keep this quantity as a constant and I do the derivative with respect of that, and I am calculating that the result is the vector, this object here that is a vector, that is this object. But then I have not to forget that the vector of the quantity with respect of which I'm doing the derivative is also here. And so I have to keep this part as it was a constant and doing the same procedure, taking the derivative with respect of that, all right? And making as a result what? Making as a result the quantity m multiplied q dot, that is the right side of this. It's like when you write okay, and you take the derivative with respect of x of this quantity. Okay, you are taking the derivative with respect of this, keeping this as a constant, plus the derivative of that one, and keeping that as a constant. We are repeating with the vector exactly what we are doing with the simple function here. And so the total will be an object like that, but this must be considered transposed because this is a column, all right? This is a row, we are taking the derivative with respect of that. We are working, what we have to obtain is a row vector for the total. What we are getting is the right part of this quantity considered as it was a constant, but the right part of this quantity is actually not a row, it is a column, because it is the first row multiplies this column that is making a number, plus the second row multiplying this column that is making the second number. So it is a column, it's not a row. We must have a row instead, because the procedure is making a row. And so the result is the transpose of that. So if you play exactly with the number, but I suggest that you have to do it with your hands. So you have to play with a small matrix of 3 by 3 and doing yourself. There is no other way to. So I can explain better in a better way, in a worse way. It is not possible if you don't do with your hands and if you don't play with your numbers, writing and spending half an hour. You will never understand exactly how does it work. So I suggest that you have to work a little bit with your hands. And so finally, the derivative of everything, the derivative of this quantity here, with respect of q dot is 1/2 q dot mass matrix vector plus mass matrix q dot transposed, that is equal to 1/2 q dot mass matrix plus q dot mass matrix transposed. All right. In case the mass matrix is symmetrical, the transpose is equal to this one, and so all of that is equal to q dot mass matrix. All right? Because the two objects are equal. In case it is symmetrical, the transpose of M is equal to M. And so you can say that the two objects here are the same. And so you can say that the derivative with respect of the vector q dot of the quantity 1/2 q dot transpose M q dot is actually q dot mass matrix, in case it is symmetrical. At this point, you understand that I have to write the transpose of that, because what we are doing, we are building the first equation. The first equation is the derivative with respect of the first element, q1. That is going together with the derivative with respect of the first element of all of that. And then in the second row, it is the second. And so when we are saying make the transpose of that, we are just saying, please write in rows and not in rows the equation and not in columns the equation. And so please make that the second object doesn't stay here, stay there. And so the reason for saying that this is transposed is in order to write correctly the first equation, the second equation, the third, and the nth equation. All right. And so what we have to do, we have to write the first equation, and so doing the derivative with respect of the first, and then the second. But we want to write everything all together. And so we write the derivative with respect of the vector q. And we keep in mind that, that we have to transpose what are the results. And so finally, the derivative with respect of the vector q dot transposed of the quantity kinetic energy is m multiplied q dot. Finished, right? So this quantity here, when the operator derivative with respect of the vector is applied to a quadratic form like that, with the internal matrix symmetrical, because we need that this matter. The internal matrix is coming from, again, the application, the application of a procedure of writing the kinetic energy or the potential energy like the one that we did. And we have this final result, all right? So all the time that we are working with quadratic forms, both kinetic energy or potential energy, the derivative with respect of the vector, that is the vector external to the quadratic form itself, is making, as a result from the quadratic form, the quantity, the mass, the matrix itself multiplied by the vector on the right side after having done the transposition. All right. At this point, we say that the Lagrange operator is asking to do the derivative with respect of time. The mass matrix is not function of time. The derivative with respect of time of this object here is equal to the mass matrix multiplying Q, two dots. All right? And so we learn once in the life that is like that. And so we calculate the energy, the kinetic energy form in the way that we did. So we are calculating the quantities here. We are doing the calculation of the elements of this matrix, and then the story is totally finished. It's totally finished because the application of the Lagrange equation is just saying that applying the operator here, derivative with respect of Q dots, to this kinetic energy that is written as a quadratic form, and making the time domain derivative, we are just writing mass matrix Q2 dot, finished. So it is totally straightforward. We are, when we wrote the energy quantities, kinetic and potential energy, yes, we know that we are writing the Lagrange equation, but if the problem is linear, and if we are working with energetic quantities that are totally fully written in terms of a quadratic form, we don't actually do all the operations that are into the Lagrange equation, because the procedure is, we do the procedure once in the life, we learn that it's like that, we learn the reasons, we learn that it's important that those matrices are symmetrical, otherwise it doesn't hold the rule. And we just write mass Q2 dots, finished. The same story, exactly the same story, works for the potential energy. I suggest that you work, if you didn't do before, you work with derivative with respect of a vector. You apply, and you apply the methodology that is the definition of the derivative with respect of a vector, and you try to work with the matrices and whatever. I repeat, it is absolutely necessary that you do with your hands. Reading in the books, listening, it is helpful, absolutely, but then finally, you have to do it. Finally, having defined those mass matrix and the stiffness matrices that are coming from the quantities that are defining the problem, as the quantities that are defining the problem are the axial action in case it is the tension of a cable, the quantities, the geometrical inertial quantities of the beam, the first order, second order derivative of the eigenfunctions, where the eigenfunctions are the solutions of the free motion of the problem. So we solve the free motion. We are getting the model shapes. We are using those model shapes in order to write that the generic displacement of the system is given by the combination of the model shapes through a newly introduced set of variables, because those are the new variables of the problem. Q are the new variables of the problem, function of time. And we use the zero order in order to write the kinetic energy that is not here. The first order derivative in order to write the potential energy of the cable. The second order derivative in order to write the potential energy of the beam. And we are calculating those numbers because those are numbers. We are now finally what we have in our hands after having done this integral. We have the numbers that are representative of the mass matrix and of the stiffness matrix. So everything is becoming numbers. And so we can write directly. We know that, yes, there is all this nice story of the Lagrange equation, but we go directly to write M Q two dots plus all right, and so the procedure is we solve the free motion problem. We calculate the modal shapes, eigenfunctions phi. If we do the calculation, if we have to do the calculation, it happens very seldom. We are working with these quantities. We are calculating the diagonal component of the mass matrix, of the stiffness matrix. Those quantities that are called K star 1, M star 1, K star I, M star I are actually the modal stiffness of the ith mode, the modal mass of the ith mode, and so we have in our hands the numbers that are representative of a concept that is the concept modal stiffness of the mode, modal mass of the mode. Early, when we were playing with the tension of the cable, we had the division that the natural frequency omega 0 I square I was something that was a fraction, and over here there was an object that is a stiffness, and down here there was another object that is what? A mass. And so we introduced the word, the modal mass and the modal stiffness, because it's changing the mode. And we had already the vision that there is something that is a stiffness that is changing the mode, a mass that is changing when it's changing the mode. But so we had this intuition, but here we have the numbers. We have the way to calculate exactly the number. And there is something else. So when we were here, when we were using the problem at the boundary condition, and we were calculating our goal was to calculate the frequencies. And we calculated the frequency, the natural frequency. We calculated the modal shapes and the natural frequencies, all right? And so we actually, the first step was to calculate the natural frequencies. The natural frequencies were the quantities that were making null the determinant of the boundary condition. When we were making the determinant of the boundary of the problem of the boundary condition, h function of omega 0, we were asking, please please work with the parameter omega 0 in order to make this determinant null, all right? And the natural frequencies were found as the quantity that we are making null the determinant, and so we suggested you to calculate the determinant function of the function, it was here, a function of the frequency. And so, and we had this very nice diagrams that you do numerically. And at the locations where the determinant was becoming null, determinant, we said, all right, this is omega 0,1. All right, this is omega 0,2, and this is omega 0n. Well, okay. And so you are very familiar with those numbers. So the natural frequency is something that is with which you played. If you are working with the matter, we gave you the code in order to make null the determinant, and this determinant was null when you are calculating the natural frequency. And so you had those numbers coming from this calculation that was strange, that was making null the determinant of a large order. So something not trivial. Well, here you calculated the mass matrix of mod I, and you calculated the modal mass of mod I. You calculated the modal stiffness of mod I. You did those calculations from a totally different way, in a totally different, make a procedure that has nothing to do with this null determinant, totally different. You calculated those mass matrix doing the calculation of M, so let's go to the stiffness. The stiffness was the axial action in the cable, the derivative of the modal shape I square, or the second order derivative of the modal shape I multiplied by EJ and so on. And so a procedure that is totally, completely different, that is linking, the two procedures are linked by being those modal shapes, the modal shape that you are getting when with those numbers, omega 0, you are going back into the formula that is telling you how you write the modal shape, and with those numbers, omega 0, 1, 2, 3, I, whatever, you are calculating those modal shapes. So the link among the two procedures is that from here you are calculating phi I function of x that is dependent on those numbers. With the omega 0 you are calculating gamma. With the gamma you are calculating the shape. And so there is a link. The link is the modal shape, the shape of the modes. So finally, making this procedure that is apparently totally different, you are calculating this number. You're calculating this number. You make the square root, and what happens? This is absolutely exactly equal to this omega 0I that you calculated like that. It is exactly the same number. But we didn't make it on purpose. We found, we made a different, we worked in a totally different way. We wrote the quantity, the energetic quantities. We wrote the Lagrange equation, and we had those diagonal matrices. And so finally, in using those diagonal matrices, for example, I'm working with all of that, and let's write what is written there. What is written there is that we write M star 1 Q1 2 dots plus K star 1 Q1 function of time equal Okay. And then you write the second is the same. M star 2, Q 2 dots plus K star 2, Q2 function of time equal dl over dq2. Okay, so finally, this object here, if you are developing, is this system, where we are positioning here the numbers that we calculate in that way. All right, but we are finding that is those numbers, the ratio of the two numbers is exactly equal to omega 0 I, but not because we are making the calculations, because it must be equal. So in the demonstration of the orthogonality, it's possible to demonstrate without making no calculation at all, just analytically, that the out of diagonal numbers of those matrices is 0, and that the ratio of the non-zero element I of the mass matrix with the non-zero element I of the stiffness matrix reversed, stiffness divided by mass, is actually the mass is analytically equal to the square of the natural frequency that was found at the very beginning of the story, making the solution of the free motion of the system. So this is totally given by an analytical theory without making any calculation. It must be like that. And so it happens that with the model approach, what is really happening is that if you have in your hands the solution of the free motion of the system, and the free motion of the system can be done also experimentally. So you are exciting a structure and you are measuring the natural frequencies. You are exciting a structure and you are identifying the model shapes. And so why not? It happens absolutely that you work experimentally on things. Typically, you are comparing and validating the numerical modeling, the analytical numerical modelization is validated experimentally, all right? But you could make the exercise of identifying the model shapes experimentally, identify the frequencies, and the left side of the problem of the model approach is written without doing anything, because you write that the left side of the problem is 1, 1, 1, because you divided by, we are dividing by m star I each row. We are dividing by m star 1 the first row. And so we find over here omega 0 squared. And so you write this, all right. No, we don't stay into here. We cancel this. You understand what I mean? I mean that I have the first row, I divide the first row times m star 1. I have the ith row, I divide the ith row by m star I. And so I get m star I at the right side of the equation, 1 divided m star I. K star I divided m star I is omega 0 I squared. M star I divided by m star I is 1. And so the left side of the problem, we can write without making any calculation, just with the free motion. The free motion is giving us the natural frequencies, and we write the left side of the problem. So the real problem is, so having the free motion that is given by the analysis of the static, of the dynamic behavior of the system, making the boundary condition, solving the problem, calculating the modal shapes, doing all of that, but actually calculating the modal frequencies, all right? The modal approach allows you to write all right, qui, everywhere is there. Everywhere is there. The modal approach is so powerful, and it is so getting the physics of the problem that allows you to write something that is totally easy. The left side is this one, is finished. It is always the same. It is always exactly the same. The real problem is to calculate the modal mass, and the modal mass was integral mass function of x Let's write like that. So the m star ij is the shape I/shape j, the distribution of mass, but we just have the diagonals, and so let's start using m star I equal 0 L m This is the modal mass. Okay, so the modal mass is the distribution of the mass of the object weighted by the square of the modal shape, and all right. Yes, so this is non-dimensional. This is mass divided by space, and this is space, and so the total is kilos. All right. So my goal today is to make you feel that the modal approach, the transformation principal coordinate is very, very powerful, and it allows us to write the left side of the problem exactly equal all the time. And the goal of our task is totally dedicated into the calculation of the virtual work of the external forces. So the difficult part of the work is to calculate that, of course. Of course, to solve the free motion in order to have the modal shapes that are allowing us to calculate the modal mass, doing this calculation here. the model shapes that are allowing us to calculate also the model stiffness, but if we have the frequency, is not necessary. Generally, we calculate the model mass. We have the frequencies, and we don't calculate the model stiffness because it is more difficult. All right, so it is necessary to stop speaking and to do the real job, that is the calculation of the virtual work of the external loads. First of all, what is the virtual displacement? I am asking to the students who did applied mechanics, and the answer, so what is a virtual displacement? Is an infinitesimal displacement of the system that is compatible with the constraints. Okay. Whatever, so what is what we should say that the most general, and so in order to say which is the virtual displacement, we say that delta y is phi1 function of x I remind you that we are always under the hypothesis that we are limited in the number of modes. But this is the limit, but is also the great advantage that we have. The limit, it means that in order to have the perfect solution of the totally perfect theoretical behavior of the system, we should make n extremely large, incredibly large, infinity, all right? But the mathematics is something, the applied mechanics is something else. And so the real advantage is that we can play with a limited, very limited number of modes usually. The modes that are actually the one who are activated by, typically, by the excitation. And so the modes that are activated by the excitations are the modes that have the frequency into the spectrum of the excitation of the force, typically, all right? And so we have a clear idea of what is needed in order to give a good representation, typically. But let's say that the virtual displacement, it is an infinitesimal displacement. It is compatible with the constraints because the model shapes that we are using are fully compatible with the constraints because it were calculated applying the constraint to the partial derivative equation, to the PDA, all right? And so it is actually an infinitesimal displacement, distribution of displacement made by the superposition of all the model shapes, each of them multiplied by the infinitesimal variation of the coordinate, of the principal coordinate associated to the model shape there. All right, so in the general way in which we are writing the virtual work, let's save space. So this F here is force per unit length, right? This is Newton over meters, all right? So you please keep you trained in receiving the question, which is the dimension? We are always asking you which is the dimension of the quantity that you're dealing with. Why I giving to myself this question? Because here I remember that I have to say, all right, so the work of the infinitesimal quantity f function of x at the time t multiplied dx, so f function of x time multiplied dx, this is a Newton, because f is a Newton over meters. And so the infinitesimal work is made by the force on the infinitesimal length element dx, multiplied by the amount of movement. The amount of movement, if it is the first mode, it is going down like that. But this amount of movement is scaled by dq1. So the infinitesimal work associated to the infinitesimal displacement delta q1 of the principal coordinate delta q1 is delta q1 multiplying this quantity. And this quantity is the distribution of mass, the distribution of force, multiplying the displacement. The displacement is the model shape 1 multiplying the principal coordinate delta q1. Sorry, here I canceled. I canceled the q. So here it was. Let's write y All right. So what I'm doing, I am making the force, the infinitesimal force, f function of x and time multiplied by dx, to work by the displacement. And maybe it is better to describe that I have this is dx, all right? This is the force. This is the quantity dx, all right? And I have the mode. This mode is phi1, and so I am moving it times delta q1, all right? And so looking at the mode 1, I am making it move by the quantity that is phi1 function of x, phi1 function of x multiplied delta q1, making it work through the force at that location, force at the same location x multiplied by dx, but I have to extend all of that to all the distribution of the force. And so it is the integral over dx of the distribution of the force multiplied the modal shape phi1 multiplying delta q1. Okay? If I have a concentrated force. For the concentrated force, the contribution delta L, the contribution into delta L of the effect of the concentrated force will be F at the location xj, function of time, this is Newton, multiplying the displacement. The displacement will be phi1 at the location xj, multiplying delta Q1. So the contribution into the virtual work of the concentrated force applied at the location xj is the scalar product of the force times the displacement. Then here we are working with something that is always aligned. If we have forces that are not in the same direction of the displacement, we have to make the scalar product. But this is obvious, so we don't stress all of that. So the contribution, if I am moving just the first coordinate, but if I am moving all the other, I have all the contribution. I have f xj, function of time, phi I at the location xj, delta qi plus. So I have all the quantities. I have the contribution of all the modes because I'm saying that I want to play with the most general virtual displacement, where all the infinitesimal variation of the independent coordinates, principal coordinate q are activated. So I have delta q1, delta q2, delta qn I, whatever, all of them. So the virtual work is the overall. But what do I have to, what the Lagrange equation is asking me to position for the first row? Let's work with the operator. The operator is asking derivative of the virtual work with respect of the vector qi transposed. So here what was written is dl over dq vector transposed. What does it mean? It means the same story that we did for the matrix, for the mass stiffness and whatever. So it means that in the first row I will have the partial derivative of the total virtual work with respect of the first delta q1. And in which way I do all of that? In which way I write the partial derivative with respect of the variable qi? Making null of the others and just dividing by delta qi. So if I have to write the partial derivative of the total virtual work that is working with all the possible variation of the coordinate with respect of the i's coordinate, what I have to do? I have to say that all the variation are null, delta q1 is null, 2 is null. All of them are null, but not delta qi. Partial derivative means exactly this. It means that you have to put 0 everything, but not delta qi, and you have to divide by delta qi. And so if I want to write what I am expecting, what I have to position for the first equation, this q1, the quantity q1 function of time will be integral 0L, distribution of force, space and time, phi 1 function of x dx plus f at the location xj function of time phi 1 at the location xj plus, and let's we forgot this load moving, that is the car, the truck that is running over the bridge. which is the virtual work of that? It is the same. It is P0 multiplying phi at which location? So if we say that at a time equal to 0, the track was here, the location at the generic time is x equal velocity multiplied by time, isn't it? So of course we have to fix our coordinate. We have to fix where it is. If there are other vehicles that are getting into, we have to take care of that. But let's consider that at a time equal to 0, the vehicle is here. The location is x equal velocity multiplied by time. Finished. And so I write what I write here is the argument of the shape functions is a value x, location, velocity multiplied by time. And this is phi1. And what is extremely interesting, but let's do it with something that is more nice for dynamics, that is a higher mode. If the mode is this one, phi vt of these higher frequency modes, higher tortuosity modes, makes a time domain function that is harmonic, that is exciting dynamically the structure just because the vehicle is moving with constant velocity. And so it is extremely interesting, in my opinion. So there are also much more interesting things around the world. But for what we are doing now here, it is peculiar to say that I have a vehicle that is moving with a constant velocity, not doing anything, very, very, very polite, but it is exciting dynamically the structure. Because I'm reading, unless we did everything wrong, but I am reading that working with the virtual work, writing the right side of the equation with the principle of virtual work, I have to say that the work is changing time at a time, and it is making a function that is a time domain function that is transforming. Actually, what is happening, we are transforming into a time domain the space domain oscillation of the model shape. And so we are understanding that the vehicle that is running at constant velocity over the bridge, actually it is exciting dynamically the structure. And if we have several vehicles that are moving this way, very correlated, so the modes are rising up unless there is nothing that is actually having bumping with the frequency over the deck. All right. Well, so let's say that we know everything. And in case we are not writing Q1, but if you are writing QI, we are just substituting I here, and this is I, and this is I. All right? So this object has a name. The Lagrangian component of the external forces. So the external forces is the distributed force, the concentrated force, the traveling load. So the Lagrangian component, this object Qi function of time, is the Lagrangian component of the external forces. And we write in this way, making reference to those simple examples, but we are focusing on a distributed load, time and space varying, a concentrated load, just varying time domain, a moving load that is just traveling. And all of that, what is very magic into the model approach is that this very complex system of excitation that is a time-space varying excitation. So this is changing in time, but it's changing also in location. This is very complex. Plus a traveling load, plus concentrated time domain forces that can be one here, another here. So all of that finally goes to one single time domain function that is exciting the right side of a 1 degree of freedom system. And it's finished. So magically, we have that the overall dynamic behavior of the very complicated continuum, and we are not making the forcing that it must be a straight line object. We didn't speak about that. We just spoke about model shapes, model frequency, free motion. But we didn't make constraints on in which way are distributed this mass. We didn't. And so what we are saying is that in a very large generalities, it is possible to write for the small displacement the dynamic problem of the continuum through the principal coordinate hypothesis, through the representation in terms of principal coordinate of the distributed displacement of the structure, with the superposition of n system, 1 degree of freedom system, excited by a time domain function that is defined through the Lagrangian component of the external forces that is described in the way that we did for those simple cases in this way. But generally speaking, what we have to say in a very general way is to write the work of the external forces as an effect of the distribution of displacement depending on the representation of the dynamic of the system in terms of principal coordinate, and to write the virtual work as the work of the distribution of external forces associated to an infinitesimal virtual displacement that is the displacement that is coherent with the constraints and that is associated to infinitesimal variation of each principal coordinate itself. There is another point. One second. Yes, please. From a concept point of view, in my opinion, is very interesting to say that what we are doing through this operation of writing the virtual work and then taking the derivative with the partial derivative with respect of the free coordinate of principal coordinate qi. So when we write dl and then dqi, so when we say I take the derivative with respect of qi of the virtual work, what we are doing in this moment, we are actually projecting. we are projecting the distribution of forces along one versor. You must have the idea that you have a field of forces and you have a space, a vector space, okay? And the excitation is for the distribution of forces is finally projected along a versor of this vector space. So the transformation in principal coordinate from the mathematical point of view is the representation of the dynamics of the system into a vector space that is a vector functional space where this operation is very, very meaningful from a practical point of view. It is like saying that we are projecting the distribution of force over the versor of the vector field that is this modal shape. Or we are projecting over this other object that is another modal shape that is another versor. So the modal shapes are the versors of the vector space that we are using in order to represent the dynamics, and the Lagrangian component of the external forces that is done in the same way that we do when we are making a projection. So we are making the work of the field of forces times the displacement when we are moving just the specific coordinate. So there is a perfect analogy for what we do into the vector fields of forces, and the meaning of this operation that we are doing, taking the partial derivative with respect of the qi coordinate of the virtual work, is exactly the projection of the very complex system of forces over this versor that is the modal shapes. There is an analogy. The mathematics can go in deep details about that, but it is so powerful because there is a very physical meaning. So the way of representation of the system through those coordinates is very successful because is very effective, is very representative of the physics of the system. When something becomes very simple, it's because it goes to the goal. Okay, and so and this is the reason. Let me see if there is something else. Yes, there is something that is missing. Who is missing? Who is missing here? There is something that we have to position here between this quantity and this quantity. Who is missing? The damping. We are missing the damping. All right. So the damping is missing. All right. The next time we are working with the damping. Okay. We stop here. If there are questions, I stay here. All right. Io spero che stesse registrando, caspita. Non so cosa dire.